Let us continue our discussion on your prime implicants and implicants. Here, let us take one more example for the continuation. Determine the number of, write down, PI and EPI. Right. Let us take this example. In this example, first listen. You can make one pair, right? And you can make one. You can make one quad. We can make one pair, and we can make another pair. Total, how many groupings are possible? 3 groupings are possible. Each grouping is called one prime implicant. Number of prime implicants is 3. And here in this grouping, both the ones cannot be touched by any other. In this grouping, this one cannot be touched by any other. In this grouping, these 3 ones cannot be touched by any other. So you can understand here, every group is having at least one minterm. At least one means it can be more than one. It can be 2, 3 also. At least one minterm which cannot be covered by, which cannot be touched by any other group. Is it clear? Every group is having at least one minterm which cannot be touched by any other group. Then it is called essential prime implicant. Essential prime implicant means how many essential are there? This group is one essential. Each group only we consider. Okay. How many number of ones are not touched doesn't matter. This is one essential. This is one essential. And this is one essential. Total 3. Or you can see here in this case all are essential. In this case, what happens is you have only one possible solution, that is for pair A bar B, C bar. For quad it is BD. For another pair it is B bar CD bar. Now you observe here what is the condition. When all are EPI, you have unique solution, single solution. So we have seen all possibilities. You can have some prime implicants, some are essential. In that case, you have multiple solutions with common terms. You have no essential prime implicants. In that case, you have completely different solutions. In this case, what is that? All are essential. In this case, what is the condition? You have single or unique solution. You have unique solution in this case. Okay, when all prime implicants are essential, we should take all compulsory, so you will get only one possibility in this case. So these are the different cases of your prime implicant, essential prime implicant conditions. And one more important point is, earlier I have given one point. In the output expression of n variable K-map, maximum how many terms are present? 2 power n minus 1 terms are present. Here each term is technically called as prime implicant. So you can say like this, in any n variable K-map, output expression contains maximum 2 power n minus 1 number of terms. Any n variable K-map, output expression contains maximum 2 power n minus 1 number of terms. Clear? Right. Now see here, one more condition. Here, suppose in this figure you may have the doubt. Sir, quad is having, it is formed by group of maximum number of combining maximum possible adjacent cells. When you take quad, pair also prime implicant, quad also prime implicant. Don't confuse. In this case, it is the maximum possibility. Here, this is the maximum possibility. Every stage we should take in that particular stage maximum possibility. Okay, so if quad is a prime implicant, don't assume that sir pair is not prime. Pair is also prime implicant in this case, but in this quad, don't take internal pairs as a prime implicant. Is it clear? In this quad, don't take these pairs again. That is, when you make a grouping, is it clear? When you make a grouping, select such that we should combine as maximum as number of possible cells. So in this grouping is made by combining maximum possibility 4 here. This grouping is made by combining maximum possibility. How many here? 2. This grouping is made by combining maximum possibility in this specific condition. 2 is the maximum possibility. I cannot join more than 2 in this case. So each grouping is called one prime implicant. Each grouping is called as one prime implicant. Copy it. Okay, next let us see one more condition. So in the question, in your classroom workbook, your question number 31, classroom workbook question number 31 in the chapter 2. Chapter 2, question number 31. Please read the question completely. Read the question. Right. What is the first question in this? Enter the logical values in the K-map for the output y. He has given y bar is equal to this. Then what is y? Y equal to sigma m of other than this, that is 1, 4, 5, 6, 7, 11, 12, 13 and 15. Y equal to sigma m of 1, 4, 5, 6, 7, 11 also, I am sorry. 1, 4, 5, 6, 7, 11, 12, 13 and 15. Okay. Now see here. Let us enter this in the K-map. S3, S2, S1, S0. It's a conventional question. What is this? Sigma m of 1, 4, 5. 1 minute please. Oh, 1 minute. 0, 2, 3, 4. So here 0, 2, 3, 4 is given. So here 4 is not present. Right. Is it clear? In the question 4 is given. So in the y bar 4 is there. Y 4 will not be there. So 1, 5, 6, 7. 1, 5, 6, 7. And 11, 12. 11, 12, 10, 8, 9, 11, 12, 13, 15. Right. 10, 11, 12, 13, 15. Yeah, this is the K-map entry. So first part is done. What is the second part of the question? Determine the PI, EPI and write down the expression for y in SOP form using minimum number of terms. Right. Let us do this. First, what is that? Determine the number of PI and EPI. Okay. You can form one pair, and pair. And there is a quad possibility also. This is one quad which is possible. So in this case, PI is equal to 5. 5 groupings are possible. How many are essential? This one is not covered by any other, this one not covered, this one not covered, this one is not covered by any other. So all the 4 are essential. But this quad, all 4 ones are covered by some other pairs. So it is not essential. Here one more important point is this quad non-essential, and also in this case it is redundant. Non-essential need not be redundant every time, but in this case it is non-essential and also redundant. Why it is redundant means because in this quad all the 4 ones are already covered by some other pairs which are essential prime implicant. Essential means what? Compulsory. When these pairs are compulsory coming, what happens? All the 4 ones are already covered. Then there is no need of this quad. So you can say like this. One important point is, when will we say a particular, here this grouping as redundant means, we say like this. A particular group is said to be redundant when all the minterms in that particular grouping is already covered by some other essential prime implicants. A particular grouping is said to be redundant when all the minterms in that particular grouping or all the implicants in that particular grouping are already covered by some other essential, then it will compulsory becomes redundant. Okay. So first copy this, I'll give you that point. copy that. Right. Now write down the point. A particular grouping is said to be redundant. A particular grouping is said to be redundant if each minterm, okay, if it is SOP minterm, POS you can understand max term. If each minterm in the grouping is already covered by some other essential prime implicant. If each minterm in a grouping is already covered by some other essential prime implicant. If each minterm in a grouping is already covered by some other essential prime implicant. Okay, that is redundant. Now in this question, what is the next part? We need to write the sum of products using minimum number of terms. Let us write the sum of products here, SOP expression for this. Right, we have 4 pairs. So what is the answer here? For this pair, S3 bar, S2 bar, S1. Next, this pair, S3, S2 into S1 bar. For this pair, S3 bar, S1 into S0. For this pair, S3 into S1 into S0. Right, this is the final output expression. Now, in this, there is another question number C. What is that? Draw the circuit for the digital logic box for using 4 2-input NAND gates for each box. They have given 2 boxes. In each box, 1 minute. In each box, how many gates are required? We need to implement it with only 4 NAND gates in each box. They have given you the boxes like this. Here what are the inputs? S1, S3, and here S2 S0, and this is your box 2, box 1, right? Now what is the question? Question C, you can see what is that? You should implement this logic circuit using how many? 4 NAND gates in each box. In each box we need to take with only 4 NAND gates. Right. Then how to do it? Here firstly, first box inputs are S1, S3, second box are inputs are S2, S0. So from the given equation, let us try to make S1, S3, S1 or S3 one side, S0, S2 one side. So let me try to take here S1 common in these two functions, and here S1, and here let me take S3 common. So here what is this? Take S1 common here and here, S1 and S3. So if you take S1 common, one moment please, otherwise we'll do one thing. Let us take here, second inputs are what? S2 and S0 na? So in these two take S0 common, and these two S2 is not common. One moment, let me check the equation correct or not. S3 bar, S1 bar, sorry, the first pair is S3 bar, S1 bar, S0. Now you see here, let us check in other also. Next one is what? S3 S2 into S1 bar, right? For this S3 bar S1 into, sorry, S3 bar S1 into S0, right? Lastly S3 bar S2, S3 bar S2 into S0. Okay, S0 is coming 3 times. One moment, let us check it again. S3 bar S1 bar S0. So S3 bar S1 bar S0, correct. Next S3 into S2 into S1 bar. Next S3 bar S1 S0. Lastly S3 bar S2 and this pair S3 bar S2. Here 1 is common in both. So what is this? S1. Now let me take in these two S2 common and in these two S0 common. So let me take it S0 into S3 bar S1 bar plus S0 into S3 bar S1 bar plus S3 bar S1 plus S2 into S3 S1 bar plus S3 S1. I can take S3 common again. One moment. S3 bar, let me take it. S3 bar S1 bar S0, right? Next, for this S3 S2 S1 bar, S3 S2 S1 bar. Next, for this it is S3 into S1 S0, S3 into S1 S0. Lastly S3 bar S3 bar S2 S1. I'm very sorry. Right. Now, what is that? If you take S0 common here, it is S3 bar S1 bar plus S3 S1. Here, if you take S2 common here, it is S3 S1 bar plus S3 bar S1. Right. Now, in this case, it is equal to S0 into A bar B bar plus AB is equal to A XOR B whole bar. So, S3 XOR with S1 whole bar plus S2 into A bar B plus AB bar. Okay, AB bar plus A bar B is nothing but A XOR B. So, S3 XOR with S1. Okay, so here you can write it in the form of A into, for easy understanding, A into B bar plus C into B. Is it clear? Just for understanding purpose. So what is A here? S0. B here S3 XOR with S1 and C is S2. Why I am writing like that is because here if you write like this AB bar into AB bar plus CB, it is a AND OR function which is equal to NAND function. We know this AND OR is equal to NAND function, right? So we'll use this later. Now firstly, what is the first condition? S3 XOR with S1. See here. It's a conventional question. It has 3 parts in it. S1, S3 are the inputs. I can give here also. What is that from? S1, S3. So let us make a XOR gate using NAND gates, which is only 4 NAND gates he is saying. We can make it. Already we discussed this in the class. Right. This is what is the output of this? S3 XOR with S1, which is our what? It is your B. For easy understanding, it is B. Now, this is the input to the next circuit. And here, 2 more inputs. What are they? S2 and S0. But what is your S2? For easy understanding, it is S2 equal to, I am taking as C, this as A, S0 as A. So what is your function? AB bar. See here. Bar means take one inverter. A into B bar plus AB bar plus C into B. Plus means take OR gate. So this is the original function. Yes or no? A into this. Actually, what is A? You know, A into B bar plus C into B. But now you observe, examiner wants only using NAND gates. So it is a AND OR function. We discussed earlier also. AND OR function can be replaced with NAND. So you can replace this with a NAND, this with another NAND. And here inverter can be replaced with a NAND inverter. So how many gates I have used? 1, 2, 3, 4. Here also 1, 2, 3, 4. With only 4 NAND gates in each box, I am able to implement the required logic function. Is it clear? Always keep it in mind. AND OR function is the same as already we discussed. What is this? NAND function. Copy it. Okay, make one note after this. Make a note. Make a note. In a n variable K map, the maximum number of prime implicants, in the output expression. In a n variable K map, the maximum number of prime implicants in the output expression is 2 power n minus 1. In a n variable K map, the maximum number of prime implicants in the output expression is 2 power n minus 1. I am not saying maximum number of prime implicants. It is maximum number of prime implicants in the output expression. Output expression is 2 power n minus 1. Now keep the heading. The next one, don't care condition. The next one in the K map, keep the heading, don't care condition. Don't care condition. Write down. Don't care condition. Firstly, listen here. What are these don't care conditions? Say in your digital design, we have certain range of inputs which will never occur. For example, you take your input is BCD. BCD means it is in the range of 0 to 9 only. But if you take 4 bits, it can be up to 15. Then 10 to 15 will never occur in this case. In this case, 10 to 15 will never occur. So, for 10 to 15, when you design the system for a particular case, your output can be anything, no problem, because these inputs will never occur. So, output can be anything means we call it as a don't care. They can be treated as 0, they can be treated as 1. If they are useful for minimization, we consider accordingly. So, what is don't care means like this. In the digital design, there are certain range of inputs which never occur. The output for those inputs can be taken as 0 or 1. The output for those inputs can be taken as either 0 or 1. Okay, we call it as a don't care condition. Right on the point. In the digital design, there are certain range of inputs. In the digital design, there are certain range of inputs which never occurs. The output for those inputs, in the digital design, there are certain range of inputs which never occurs. It depends on your design, from where you are getting the input and all. It depends on your system. System to system, it will vary. Okay. So write down continuation. In a digital design, there are certain range of inputs which never occurs. The output for those inputs can be treated as either 0 or 1. Either 0 or 1. We call it as don't care condition. In brackets, write down like this. It is the symbol for don't care, cross or X. Okay. Next line. For example, in a BCD system, the output for the inputs, greater than 9, are treated as don't cares. Next, write down next line. Don't cares are considered if they are useful for minimization. Otherwise, they are neglected. Don't cares are considered if they are useful for minimization. Otherwise, they are neglected. Okay. See here. For example, let us take one example. f of AB equal to ABCD equal to sigma m of 0 1 plus don't cares of 8 9 up to 15. Suppose they have given the function like this. Here m means min terms, d means what? Don't cares. So here sum of the min terms 0 and 1. Next, don't cares of 8 to 15. So 8, 9, 15. Don't cares are represented with cross. Now here you understand. If you don't have don't care, it is a pair. But if you consider these two don't cares as ones, because don't cares means you can consider as 1 or 0 according to your convenience. So here if you consider as ones, you can make a pair. Sorry, you can make a quad, which will be helpful for minimization. So if it is helpful for minimization, consider the don't care. Here in the SOP, considering means treat it as 1. Otherwise, these are not useful for us, so neglect the don't care. Which don't cares are useful for us? Those which don't cares are useful for us, those you consider. Remaining you neglect. You can neglect all, or you can take all, or you can take only few depending on the function given. So in this function, what is the output function f? It is for this, it is a b bar, and here it is c bar. So without don't cares, it is a pair. By considering these two don't cares, you are getting quad. So here what is the meaning? These are don't cares, they can be treated as 0 or 1. In this function, we are treating these two as ones and remaining as zeros according to this particular function. Okay, we are considering these two don't cares, we are neglecting the remaining don't cares here. Don't care can be treated as either 0 or 1. How don't care condition will occur is depending on the function. In that function, suppose these will never occur. You have 4-bit input, but these are not occurring in that function. Then you can take like this. Copy it. Okay, let us take few more questions. Okay, now see. Here, I should not take this quad. First, this is a pair, this is a pair. After pair, you can make a quad, but please listen. Whether you take this quad or not, to cover these two ones, you should take a pair. Okay. But if you take this quad, is there any use? No, because if you take the quad, already these two ones are already covered. So we are covering extra two don't cares. Instead of that, happily neglect the don't cares, because my intention, our main aim is to cover all the ones. Here all ones are already covered. Yes or no? Here all the ones are already covered. So there is no need of taking this quad. If you take this quad, we are getting one extra term which is covering only don't cares. Instead of that, happily neglect it. Then what is the answer? A bar into B bar plus AB. Okay. If you consider here all ones are already covered. If you consider this quad, extra term will come which is not required. Okay. Copy it. Copy the next question. So here you see, you can form a octet, because all ones and these two quad pairs, you can, these don't cares are considered here, you can form a octet. In this case, what is the answer? F equal to 1. If you don't consider the don't cares, you will be getting only pairs. By considering the don't cares, you can form one octet which will give me answer F equal to 1, because sum of all here will be equal to 1. So here we definitely consider the don't care. Okay, copy it. So now we can say that when don't care conditions are given, first after drawing the K-map, if it is helpful for minimization, then I consider the don't care. If it is not helpful for minimization, I simply neglect the don't care condition. If it is helpful, I'll consider the don't care conditions. If it is not helpful, I will neglect the don't care condition. Okay? That is about your don't care condition. Next lecture we'll see if two functions are given with don't cares, then how to add these two functions, or how to AND operate or any other operation, how to perform on two functions. Okay, or we'll continue in the next class. Thank you.